Alright, so this is the fourth lab, bar magnets. So the purpose of this lab was to better understand the distance-dependent magnetic field of a bar magnet and to measure the magnetic field both on and off axis from Biot-Savart law, and we want to simulate these through GoScript. The magnetic dipole moment we found was roughly 7.265, and the n value, or the slope of the line that we found, was negative 2.0232. So some key concepts here were Biot-Savart's law, which describes the magnetic field due to a small segment of a current carrying wire. And for the purpose of this lab, we wanted to use two equations specifically. One to find the magnetic field due to a dipole, and the distance dependence formula, which can be seen here, and we're going to use that as a graph later on. So our assumed model and assumptions are: we assume the bar magnet acted as a magnetic dipole, and that the magnetic field that is generated weakens as distance increases. And the bar magnet, you can kind of see what it should look like down here. It's a visual model. Alright, so the initial conditions of this experiment were that the system was the bar magnet and observation point, and the surroundings were everywhere outside. Initially, the magnetometer chip location was found by sliding the phone perpendicularly in both horizontal and vertical positions, and then once it was found, both on-axis and off-axis dipole moments were found by measuring the distance between the bar magnet and magnetometer at multiple distances. Alright, so for the first part, we have the on-axis with the values found at different distances on the meter stick, and we were able to generate a line using the following equation here, which measures the slope, or the n value, which is what we got right here. And these were the averages, and they're calculated natural log values. And for the off-axis field, we found the distance by putting it perpendicular, and measured the magnetic field by the Earth, the magnetic field at the x position, and corrected y position and z positions, and to find the net magnetic field. Alright, so for the calculations, first we needed to find k, which can easily be found from the y-intercept of the function we graphed. All you have to do is solve for k using ln of k equals negative 13.442, and you get k. And you can find the dipole moment by setting r equal to 1, and we got that to be 7.265. Alright, so the computational model here, you can see the first half of the code. We wrote the dipole field function right here, and then here we were able to put all the distances. This is just the model continued. All this does is kind of create the arrows and prints out the results. And here you can see the calculated B field magnitude and the percent difference, and the at 45 degree distance d. From what we observed, the following two statements are true. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And we were also able to find the B field at 45 degree angle at distance d, and that is that vector below. Other electronics in the area could have skewed the data, and the exact location of the magnetometer was not correct, and those could have been the two errors here. Alright, so for the what ifs, what if we hadn't oriented the experiment to compensate for magnetic north, and instead just laid out the meter stick at some intermediate angle with respect to the Earth's magnetic field? How would our results have changed? Well, the Earth's magnetic field would then interfere with the bar magnet's magnetic field, since it would read both, and that would create a curved line. And what if we were to stick two identical magnets together end to end and run the experiment again? How would the measurements differ? And this would essentially double the magnetic dipole moment, but the direction would remain the same. So the slope would remain the same, but the k-value or y-intercept would change. All right, that's all I have. Thank you.